kilopascals, I think it gives approximately 55 units per amp. So it does.
So you're using pneumatics?
Yeah, pneumatics, yeah. But the idea behind this is like the actuators currently are like pneumatics based. So they can be, the methodology is the same for any kind of actuators. I do undergrad in Alberta University.
3 years ago, So which campus in Alberta?
On the Stony. So Raha happened in
Were you there?
No, I wasn't there. I was here. But I saw it.
All right, okay, we'll get started.
Yeah.
Good morning, everyone. Welcome to day 2 of the Kinematics Summer School. We had a great first day. Would you agree? Yes? Oh, wake up. All right, so today we have 5 presentations. We will exceed our time duration from yesterday by 15 minutes. I hope it's not too much of an inconvenience, but it's in the schedule, so we're not changing anything that's not in the schedule. For the first session, we have Professor Jeff Gurr from Stony Brook University. He's going to talk about Quaternions and Clifford Algebra and its application to kinematic synthesis of mechanisms. After him, we have Professor Shanwen Kong in the second session, and he'll talk about parallel mechanisms and how you synthesize those. In the afternoon, we have a session from Professor Chakravarti and myself on machine learning, fundamentals and applications, and finally we'll end the day with a talk by Professor Jim Schmiedler, who will talk about optimization and synthesis. So I think we are going to swing between the two extremes of covering tools as old as Quaternions, more than 100 years old, to machine learning, which is the latest tool for engineers. So let's welcome Professor Gurr.
Good morning, and welcome to the morning session of Kinematics Summer School. And I heard that yesterday we had a fantastic day of all the workshop, was the hands-on experience, cool gadgets, and I don't think I can top that. And this morning's talk will be highly theoretical. Before I proceed, I would like to acknowledge 2 people, and without which this will not happen. And the first one is Professor Mccarthy. He's my PhD thesis advisor. I learned everything about Quaternions and Clifford Algebra from him.
And I learned everything from him.
I was gonna say, if I made any mistake here, it will be all your fault. He beats me. So the second is Professor Anurag Purwar. He's a colleague in our department. Actually, much of the slides are from him. I added some of my own, so that's why I put his name there.
So I should add that I learned everything about Quaternions and Clifford Algebra from Jeff.
So indirectly it goes back to my
I was not going to say that.
So if you have any questions, I'll say. Okay, so here are a list of references. First one, of course, is the book Theoretical Kinematics by Bernie Roth. Some say that this book, every chapter can be a PhD thesis. So it's very deep mathematically, and Quaternion is just one chapter of the book. Okay, and then of course second one is by Professor Mccarthy. It's intro, because the first one is so deep. We need an intro, and Mike has done that. Then there are also additional books on Quaternions, and not necessarily from kinematics community, from others. Okay, so Quaternion algebra, what is the root of that? And typically people say, well, it begins from complex numbers, which is taught by basically everywhere. Okay, so we are gonna begin with a review of that. Then we're gonna talk about algebra of quaternions and geometry of Quaternion algebra. So we're also going to talk a little bit about Athenian vector basis, because we're dealing with point transformation. So we'll have to talk about that. Then we're going to talk about dual Quaternion, which is an extension from three-dimensional rotation to spatial displacements, and also planar quaternion as a special case. We are also going to present a few examples how they are used, and finally we're going to talk about Clifford algebra, how it's related to quaternions. So complex number, that's well known from the class that you have took. Basically, it's saying that it's an extension of the numbers that we have learned. Initially, we have integers, counting apples and oranges, right? Then we have rationals, fractions. Then we have real numbers that occupy the entire real axis. And then the next one is complex number. At least when I was in college, the idea of complex number is always very odd. All this stuff makes sense intuitively. And for complex numbers, the idea that imaginary unit I squared equal to -1 just doesn't make sense. Square of something has to be positive. Why this is negative, right? I accept it because that's my professor taught me, so I'm not going to challenge that. Okay, but I always question that, and this is really the root of what we want to discuss. Why I squared equal to -1? What does that mean geometrically? Okay, so if we have a good handle of that, the rest will be easy. So this is just a recap of complex numbers. So you have a point in the xy plane. Instead of having two unit vectors, one in x direction, one in y direction, we represent with a real axis and with imaginary axis, and that will give rise to complex numbers. And you can write them in polar form, which is in terms of the length of the vector as well as the angle, right? And you can write this e to the I theta in terms of cosine theta, plus I theta. And that's also, we also take this for granted, right? That's, Then complex number is an algebra, right? So it satisfies the conventional rule that we have, okay? Closure meaning if you add two complex numbers, the end should be a complex number of the same type, right? And associated meaning if you have three complex numbers, you could add any two of them first and add the last one third. It's not going to change. The order with which you add them doesn't affect the end result. Commutative is when you multiply them, okay, which one you put first, which one you put next, doesn't affect that. Distributive is sort of a combination of these two. If you have a scalar, and that you can multiply through it if you have multiple complex numbers, okay? And you could add, you could multiply, and identity in this algebra is basically 1. Basically, what mathematically in the abstract way is that what is identity? Anything that times that thing is equal to itself. Okay, it can be a number, can be something else. Okay, as long as that holds true. So this is sort of a basics of algebra. Now, all this are basically from textbook. Okay, so you have a vector, right, and we can represent the vector in complex number form, and this is the equality that we mentioned before. Now, if you multiply two complex numbers, okay, the end result is that their length gets multiplied and their angle got added together. Okay, you have a new vector such that the length is the product of the magnitude of each one, and the angle gets multiplied. Okay. So now the key thing, the most useful one is that if you have one of them is a complex number such that the length is equal to 1, then the effect is just to change the angle. Okay? And that gives rise the idea of a rotation operator. Okay? Now, another representation of row commutation. So this is the algebra, so I'm not going to go through it. And in the end, you can represent the rotation in terms of matrix as well if you use Cartesian coordinates. Okay. In terms of complex number, you are basically doing e to the I alpha times the vector, right? And here's the matrix that times the vector, and the net effect is the same. So the question is, what does that tell you? Okay, what does that mean? It turned out that if you look at this matrix, okay, it can be decomposed into two parts. One has a basis of this identity matrix, and the other one has a basis of this 0, 0, and you have 1 and minus. It's a geosymmetric unit matrix. Now, if you multiply these two matrices by itself, this should be -1, sorry. Okay, this time itself is equal to the negative of this guy. Okay, so that this rule is the same as I squared equal to -1. Okay, the only difference is one is in terms of imaginary unit, the complex number algebra, and this one is in terms of the matrix algebra. Okay, so that's one thing. Second thing is, now how do we get this thing? So if you look at rotation of 90 degrees, if alpha is 90, then cosine alpha is equal to 0, right? Sine alpha equal to 1. So when alpha equal to 90, this matrix is equal to, this, okay? When alpha equal to 0, that means no rotation at all, then you get the identity matrix, okay? What this one tells you that this is the rotation operator that rotates a vector by 90 degrees, okay? In fact, this is the interpretation that Clifford had in his original paper on Clifford Algebra, I think in 1860 something. Okay, after Hamilton wrote his book on paper on Quaternion. So Hamilton approached Quaternion purely from an algebraic reasoning, okay? And Clifford handles that purely from a geometric reasoning, okay? And I think it's the geometric reasoning that makes a lot of sense to us as people who work in kinematics, okay? So, and we will come back to it. Now, there are a lot of papers on quaternions and what means and how it interpret. If you do it from an algebraic perspective and you try to interpret it, it's not so easy to understand because it involves four-dimensional space. Okay, we will talk about. You will see that it's not so obvious. But if you look at it from matrix representation, then it becomes very obvious from a rotation operator perspective. The other one that I want to say is that when you have an exponential function, you can do Taylor series expansion. So if you do Taylor series expansion, you will basically get this formula. Likewise, you can also write this as a matrix exponential and do a Taylor series expansion, and then you will get something like this. So here's a slide that capture what I have said. I is actually a rotation operator of 90 degrees. So if you have a vector, okay, you apply I to it, it will rotate that vector by 90 degrees. If you apply once again, it will rotate another 90 degrees, which will give you 180 degrees. And that's why you have an opposite sign. And that's why I squared equal to -1. And that makes sense, right? You rotate 90 degrees twice, you change the direction of the vector. Okay? All right? So in fact, in Clifford's original book, he has this operator, square of that operator can be either -1 or +1 or 0. Okay? There are three possibilities. Okay? So it actually corresponds to different geometries. Okay? So it's essentially that is the link between Quaternion and Clifford Algebra. Quaternion only consider the case of I squared equal to -1. Okay, so this is the historical, the slides about the history. Hamilton was the first one. We all know complex number. Then he was thinking complex number works so well in the plane. How do I extend it to three-dimensional rotation? He tried and tried. He tried to form a complex number with three dimensions, not two. Then he has a problem because the product of two complex number with three components will have the fourth component. And we know that it violates the closure property, right? So it cannot be an algebra. So the only way he could make it work is to start with a number with four components. That's why I call it quaternions. Then a complex number with four components, if you multiply by another one of the same kind, will also give you a complex number of four components. Okay, basically that's what his discovery is. Now we don't think it's a big deal, but back then it was a big deal. That's a conceptual breakthrough. Okay. It's called hyper-complex number because it involves more than two coordinates. Okay, here's the algebra presented in the way of Hamilton. Okay, so basically you have four components, and the first one is real. You have three imaginary units. I, J, K, each one is a rotation operator. Okay, any vector multiply either I or J or K would rotate that, vector by 90 degrees. Okay? And if you do it twice, of course, it's going to rotate by 180 degrees. So they all have this property, I squared, J squared, K squared, all equal to -1. Okay? And now, the other rule that you have, because these three rotation, vectors are considered to be perpendicular to each other. So in order to make the algebra work, we also define ijk equal to -1. So these are the basic rules. Then here the term, permutation ij equal to k. If you, reverse the order, it will change the sign. Okay, and same goes true for the rest. Now, if you look at these rules, they look very much like vector cross product, right? I cross j equal to k, etc. Okay. In fact, Quaternions were invented before vectors. Clifford Algebra were invented before vectors. Okay. Vector is a simplified version of that. Okay. So product of two Quaternions, once you know these rules and you multiply them, okay, you apply the rule and you can write down what the results are in what appears to be a vector form. Okay, here is we are overloading the symbol here, right? So Q and P here, we really mean vectors. Okay, so it's a vector dot product, and here is a vector cross product. Okay, so this is a scalar part of it. Okay, and this is a vector part of it. Okay, so we have vector Quaternion first before we have vector. Okay, so that's the history. Okay, so this is the summary, and you could show that even if Q4, P4 equal to 0, okay, so we have two vector Quaternions, and you multiply them, so this will be equal to 0, but this is not in general, unless the two vectors are perpendicular. So that's why you always have the fourth component, and that's why we need Quaternions, not, I don't know the word, Quaternions or whatever. We don't have that. Okay, we only have Quaternions. Okay, so here are just additional explanation what the Quaternion products are. Of course, if you reverse order, that's essentially is a vector cross product. Okay, this just means that they don't commute. Q times P is not equal to P times Q. It's a non-commutative ring. Okay, it's less than the algebra. And once again, we can have a scalar component and a vector component as well. Okay. Now here it says if we have two vector Quaternions, okay, if we multiply them, then they can be written in this very nice form. And first part is the scalar product is a scalar, and this is a cross product. Later on, people have dropped this, and that will give rise to the vector algebra in terms of instead of Quaternion algebra. Okay, that's what we have in top. Now, the other one is that we also want to look into about multiplying a Quaternion with a vector. okay, and how that may, affect the movement of the, vector, okay? The whole purpose that we are interested in, quaternion is because it can represent rotations, right? So if we have a quaternion, we multiply by a, vector, what does it do to that vector? Same way as if we multiply a complex number, unit complex number to another vector, it causes the vector to rotate in the plane, in the same plane. So the question is, if we have a vector in the plane that's oriented in 3D space, okay, not one of the coordinate planes, and we apply a quaternion to it, what does it do? Okay, so this is, what the explanation is. Now, and we are going to coming back to, this. The other way is that it's less commonly used in kinematics, but in physics textbooks, sometimes you see that a quaternion is represented in this form. So you have a pair of complex numbers. Each unit is a complex number. You have two of them. Then you combine them with another imaginary unit, j. Okay, that's another form that you can find it in some textbook. Basically, a quaternion is a combination of two hypercomplex number. You have a complex number alpha, complex number beta, and then you write them in the complex number form. Okay, and then you can apply the same logic that you have learned in complex number to manipulate quaternions. Okay, for example, you can define the conjugate, okay, and all that. More, okay, so if you have a quaternion and you multiply by its conjugate, which means that the imaginary units I, j, k are replaced by minus I, minus j, and minus k, okay, and you multiply them, this will give you the norm of the quaternion, okay? And then we can also define the inverse, okay? Since quaternion is an algebra, we have an inverse, and so q times its inverse has to be equal to 1. And in this case, doesn't matter which order you do the calculation. And 1, of course, is the identity in Quaternion algebra. This basically shows the derivation that, okay, then if you multiply both sides by q conjugate, you will get this equation. Then q conjugate times q equal to 1. And that's how you define the inverse of a quaternion, which is conjugate divided by the norm. Okay? This form is very similar to complex number, right? That's how you define the inverse. Okay? Now, if n equal to 1, we have a unit quaternion. Okay? And so here we know that the sum square will be equal to 1. So that means if we let this one to be cosine square, and the rest of them can be called a sine square. Okay? So that's an algebraic trick that we use here. The next page will show you why it makes sense. Okay? Then you can actually write a unit quaternion in this form: cosine theta plus sine theta times a unit vector quaternion. Okay? Where the length of u is equal to 1. Okay? And this is also well known, tied to the Euler parameter of the Brook limitation. So this is a different way of looking at it, okay? Then we can write this in exponential form, okay? Now, this also means that if you multiply a unit quaternion with another, quaternion, the length, does not change, right? So this will give rise saying it's a rotation operator, right? Okay. Now, here is saying quaternion multiplication is a linear isomorphism. That's a big word in 4D space. Okay. What it means that the length does not change. That's all it means. When you apply a unit quaternion to a vector, you multiply it. Okay. It changes the original vector in such a way that the length doesn't change. So if you consider a space, you have a vector that changes. However, it changes, but the length remains the same, and we call that to be a rotation. Okay? So now the question is, what type of rotation is it? Here's a slide just to make a comparison between quaternion plane and complex plane. Now back to complex number, if we apply a complex number, a unit complex number, to another complex number, which represent a vector in the same plane, and you will basically rotate this vector in the same plane, okay? And this turned out to be true for quaternion as well. If the rotation operator and the vector are in the same plane, you apply to it, it will create a rotation in the same plane. Okay. Now the question is, what if the vector and the quaternion are not in the same plane? What does that do? Okay, that's the challenging part. It's hard to visualize. Okay. So basically, you could view that if you have a plane in the three-dimensional space. One is you have a plane in this plane. You have both. You have quaternion. You have a vector. Multiply. Everything is good. But what if this plane is in the 3D space? You also have a quaternion in the plane, you have a vector in the plane. Well, in terms of geometry, it's the same. It doesn't matter whether this is one of the coordinate plane or generally oriented plane. It doesn't make any difference, right? So basically, you can view that in this particular case, a quaternion is just a 3D representation of a complex number operation. There's nothing new there. But you do have something new that if you have a vector in this plane and quaternion is not in the same plane, then you have a truly 3D operation. One is a 2D operation described in the arbitrarily oriented plane, and one is a true 3D operation. And that's a part that's new. Okay, the complex number cannot handle it. And that's why we need quaternion. Now this is a slide that I copied from one of my paper that describes matrix representation of quaternions. Okay? So the paper starts with a skew symmetric matrix in 4D space, okay? And it turned out that we can represent this in this vector form, okay? Here we only have three components, n1, n2, and n3, right? So we can represent it in this form, and each one is a 4x4 matrix. Okay, I, J, and K, and they only consist of 0 and 1, and they are skew symmetric. Okay, so if you let M1 to be equal to 1, you let M23 to be equal to 0, you will get this one, right? If you make M2 to be 1 and the rest equal to 0, you get this one. And the third, M3 non-zero, you get, K. Okay? So these three are obviously, basis vectors for this algebra. Okay? And it turned out that if you multiply I matrix with itself is equal to minus E, where E is a 4x4 identity matrix. Same is true for J and K, and I times J equal to K, equal to minus J and I. So it fits with Quaternion algebra, the unit small ijk perfectly. Okay. In fact, this is the matrix representation of Quaternion units. Okay. Now, we have said that if we look at a subset, this one is a two-dimensional matrix representation of the complex number, imaginary unit I. Okay? And that represents a 90-degree rotation in the plane. Okay? But here we have two of them. We have another one here. And they're in two different planes. And these two planes, if you consider this to be a four-dimensional base, these two planes are orthogonal to each other. Okay? So you could imagine that we can say I represents rotations in two orthogonal planes. Each has an angle of 90 degrees. So we have four dimensionals. Now this takes a little bit extrapolation. In three-dimensional space, you have a plane, then you have a vector, right? And that represents the three dimensionals. And the vector is perpendicular to the plane. In four-dimensional space, you have a coordinate plane. You have a plane, not just a line, that's perpendicular to the given plane. What does that mean? It means that every line in this plane, however, whatever orientation that you pick, every single line is perpendicular to this plane. Okay? That's unique about three-dimensional rotation. You do have a unique axis. Okay? In 4D, you don't. You have a plane of axis for rotation, basically. Okay? So here, basically saying we have two rotations of 90 degrees, and that's the key for understanding Quaternions. Okay? Any questions about this? No? Okay. So you can view this is a matrix representation of a vector Quaternion. Okay. Then my next question is, what will be a matrix representation of a general Quaternion? Well, you will have M4, right, times 1. That will make it to be a Quaternion. So 1 here is the identity matrix. That means you are going to add M4 to the diagonal term. Okay? So this will be a matrix representation of a Quaternion. Okay? Now, if you have another matrix of the same form, but with different sets of numbers, instead of M1, M2, M3, M4, you have, let's say, P1, P2, P3, P4, and you multiply them, the matrix that you will get will be the same form. exactly the same form, and that also shows that it's algebraically closed. Okay, that's the I don't have the slides, but I do have a paper on this I can provide you if you are interested. Okay, so now what follows is try to explore this from a purely geometric turn. I know it's hard to visualize this. That's why I gave you this. Okay, this is much easier to understand. But if you read most of the books written by others are Quaternions, these are the reasoning that they will go through. Okay, basically saying, okay, what about Quaternions in a complementary perpendicular plane? By complementary perpendicular plane, meaning the plane that's orthogonal to the given plane. Okay, all right. How are they affected by a unit Quaternion algorithm? Okay, so I'm not going to read through this. So if you have a Quaternion, we mentioned that a Quaternion involves a rotation axis u, right? That's what we all know. The angle of rotation theta, right? Okay. So if we apply this to another vector, what do you actually get? Okay. Now, from this, we basically know that it represents a four-dimensional rotation in two mutually orthogonal planes of angle theta. Okay, there's one rotation angle theta in this plane, another rotating angle theta in the other plane. So it involves two, not just one. Okay? Okay, basically that's what it's saying. Okay? So I'm going to skip through this because it's not so easy to follow. Now the key that I want to get is a 3D rotation. Okay, where's my slides? Okay, so let me just say so when you want to rotate a vector in 3D space using Quaternions, and we all know that the formula is, let's say P is a vector, Q is a unit Quaternion. The formula actually is a QP times Q conjugate, right? That's a well-known formula. So the question is, why do you need to do that? Why can't we just do Q times P and be done with it? Okay. First of all, Q times P will give you P is a three-dimensional vector. Q is a four-dimensional, full-fledged Quaternion. Q times P is, in general, another Quaternion. It won't give you a vector Quaternion, so it won't work. That's what Hamilton has been struggling with, right? So you have to do more to make it work, right? So the more you do is you multiply another one, a Q conjugate, after that. Okay, so now Q times P, we already know it's a pair of rotation in 4D space. And P times Q conjugate is also a pair of rotation in 4D space. Okay, so we pick them to be the same, but it's conjugate to each other. So what does that mean? That means you are going to reverse the sign for one of them. Okay, it's a combination of conjugation. The other one is you multiply versus post-multiply. If you combine these two, what happens is that the combined effect is you have a rotation twice in the same plane. So the angle will become 2 theta instead of theta. Okay? And on the other plane, you have the first one have a rotation of angle theta. The second one will have a rotation of angle minus theta, and they cancel out. So in that case, a 4D rotation becomes a 3D rotation. Okay, and that's what this is. So people will always say, Quaternion represents a 3D rotation. Technically, that's not quite accurate. Quaternion itself represents a 4D rotation in 2 orthogonal planes. It's the combination of these two give you a 3D rotation. Okay, that's the whole point. That's what Hamilton has been struggling with, right? So Quaternion times a 3D vector in general will give you a 4D vector. But if you pick them carefully, okay, involve pre and post multiplication, you could get a 3D vector. And there's only one way of doing it, and this is the way, and that's why we're using it. Okay? Any questions about this? Yeah.
This shows some of the field. So what does QP equals to PQ?
Yeah, this is not quite correct. Okay. Yeah, QG is not equal. It's under special cases. In general, it's not true. Okay, so these algebra basically saying if I multiply Quaternion before that, and this is the result. If I multiply a Quaternion that's after a vector, and this is what you get. And if you multiply a Quaternion with a conjugate, and this is try to show it algebraically. Okay. This is another attempt, okay, basically saying that we have 2 orthogonal planes, and this is one of them, okay? If QP will, basically rotate this thing in one direction, and P times Q conjugate will rotate the same vector in the opposite direction, and they cancel out, okay? Here's a example, basically saying that when you apply Quaternion operation Q times V times Q conjugate, where Q has a rotation angle theta, sine theta, cosine theta, the end result is a rotation of twice 2 theta. Okay. Here's a example. This is a unit Quaternion that represents the rotation axis, right? And theta is a rotation angle, and we can use that to form a unit Quaternion, okay? And the length happens to each component happens to be the same. It's a nice number to work with. Then you apply the conjugation, QV times Q conjugate, then assume that the vector you want to apply the Quaternion operation to is a unit I. You multiply them out, it will give you J. Okay? So what does that mean? It rotates this vector out of the 1I plane. It's a 3D rotation. Okay? All right. And the rotation, the vector itself rotated by 90 degrees from I to J. But the rotation angle for the quaternion is not, right? It's 2 pi by 3. If you multiply by 2, it will be 4 pi by 3. So then you will ask, what's going on? If this is 90-degree rotation, shouldn't the rotation angle be 45 degree? Or 135 degree? Well, the reason is the two vectors are not in the same plane. So let's look at, this is the 1i plane, let's say, right? You have a unit vector I there. And this one is pointing out of the plane, and they make an angle, okay? So you have a vector, I wish I can draw, but I cannot, draw it. So you could have a vector that rotates, if you just look at this. If you have a vector, this is I, and this is J, let's say, rotate by 90 degrees. But the rotation axis is not perpendicular to this plane. It makes an angle. So it's possible that this quaternion rotation is not 90 degree, but the actual rotation in this plane is a 90 degree because it's a 3D rotation. Okay? That's make it hard to visualize. Okay? But amazingly, this algebra works, so you don't have to visualize it. You just apply the algebra. If you don't make any mistake, you can be assured that the answer is correct. Okay, does that make sense? Okay. So if you have a quaternion such that its rotation axis is perpendicular to the plane, then the rotation angle has to be the same, 90 degrees. We already showed, right? So if it's not perpendicular, okay, so we have shown that you need to multiply twice, Q and Q conjugate, okay, and that rotation for the entire rigid body, if you consider this as part of the rigid body, is actually 2 theta. Now, it's possible that there is a line in the rigid body, the angle of rotation could be more than that or less than that. Can be different, depends on the orientation of the line. If the line happens to be aligned to the rotation axis, it's not going to change at all, right? If it's perpendicular, it will have the maximum change. If it's somewhere in between, the angle of rotation will be somewhere in between. Okay. Any question? I know it's a little bit abstract, and sorry I don't have the nice graphics to show you. I was gonna use my finger to draw things, but I couldn't. Okay. So, okay. Now there's another one. Is a matrix form of quaternions, and the name is a little bit confusing because this matrix form is not what I have just mentioned, 4 by 4. Okay, this is the matrix representation of 3-dimensional rotation. So we know that if Q is a unit quaternion, if we multiply a vector quaternion in this way, we will get another vector quaternion, okay? And if you expand them out and you put them in matrix form, this is what you have, okay? It's well known, it's quadratic in quaternion components because we did it twice, okay? And it has to be an orthogonal matrix, because it represents a row permutation. Okay. And this is in homogeneous form because it's a 4x4 matrix, and this is a 4x4, four-dimensional vector, and we call it homogeneous coordinates. Now compare this with the matrix representation. For matrix representation, if you use A11, A12, etc., right, you have 9 components to work with, and 9 components they are not independent, right, because it's an orthogonal matrix. You are talking about these 9 elements with a set of constraints associated with it. Algebraically, it's not so easy to handle. You have more coordinates, more numbers to deal with than you have relationship. But if you're using, Quaternion, you only have 4, and there's really no 4 will be. If you consider them to be homogeneous, they're independent, right? So it's very easy to work with. So it's compact, and it's efficient to do the calculation. The number of operation is 16 versus 27. Now you may say, well, here you have more multiplications than matrix form. It would be a combination of multiplication and addition. Okay, so you will say, if you know a little bit about how CPU works, right? Current CPU typically design up, addition costs less than multiplication and division and all. So, whether this is indeed fast or not depends on how the instructional set is designed. But it's possible that you will design a CPU that multiplication is the basic thing, and it would be faster. But nonetheless, it has less operations than the matrix form. Okay, and you can normalize them easily. Okay, because of Quaternions. Okay, and the last one is that because the Quaternions are independent components for them. So if you want to do interpolation, it will be very easy, okay? Which is something that we will talk about in the next slides. And here's one example. Let's say you have 2 orientations in space, right? So let's say this is one, and this is another one, and you want to find a row permutation that connect the first one to the last one. You could do it using matrix formulation, and if you just do it blindly, if we have a point A and B, and if you want to draw a line between the two, it will be 1 minus t times A plus t times B, right? If it's a point. Works very, very well, right? Now, here is a matrix. If you try to do the same thing, and then you have a problem, is that the end result is not an orthogonal matrix. R0 is, R1 is, but RT is not if you apply it. So you will have to go through a normalization process. Orthonormal, you need to make sure the coordinate vectors are perpendicular once again and all that, right? It's very costly to do that. It also distorts the rotation as well, okay? So geometrically, it's not a good thing to do, and algebraically, it's very costly. Now, if you use Quaternions, first orientation is represented by one Quaternion, second is another one. You do linear interpolation. It still has 4 components, right? Okay, And they don't have to be a unique quaternion, which this one is not, because our matrix representation is homogeneous. We automatically divide this. So Q does not have to be a unique quaternion here. Okay. All right. Any questions? Now, there's one drawback is here we do a linear interpolation of this two, right? Okay. Instead of it changes the length of the quaternion, okay? It will change the speed during the motion. So when you rotate from the first position to the last position, the speed wouldn't be the same, because this process will create slow down and moving faster, accelerated the accelerate process. Now, there is a way of creating a uniform speed interpolation. And the way you want to do it is that you want to do an interpolation such that the length of the unit quaternion doesn't change. It remains to be a unit quaternion. Okay? And you could do that. This is called a spherical linear interpolation. And this is, the first paper on this is by Ken Shu made in computer graphics in 1985. Okay. So this is the formula that he has come up with. Okay. Where theta is the angle between the two quaternions. Okay. And you can write this in quaternion product form as well, purely in Quaternion Algebra. Okay. Any questions about this? Now, this, of course, computational cost is higher. You need to compute the angle between the two. You need to compute the sine of that. Computational cost is higher than just to do 1 minus t and t. Okay. But it does give you uniform speed. And the other thing about what's nice about this formulation is that in TAD we have Bezier curve, B-spline curve. These are all based on repeated linear interpolation. It's called Quaternion Algebra. Right? Everything is based on repeated. So because this is in polynomial form, if you repeat them, you will get a polynomial of a higher degree. Okay, that's why you get Bezier curve. But if you do spherical linear interpolation, mathematically it's not so nice. Okay, yes, it does give you a smoother motion, but computational cost is high. You don't have a nice mathematical representation of them. Okay. Any questions? Do you want to take a break? Everybody? Okay.
Well, Jeff, if you want to take a break, we can do that.
I'm fine.
Can you do something? Maybe it will help if you have the microphone attached.
What?
We have a microphone. I forgot
Oh,
about
okay.
that.
Okay. Can you hear me in the back?
Yeah, no, it's actually for you, so that
Right, I know.
you don't have to keep that on.
Okay. Can you hear me better now? I can hear my own echo now. Okay. So here's Bezier curve that I've talked about. So we can construct a Bezier quaternion curve just like any Bezier curve. A typical Bezier curve is in 3D space. Now it's in 4D space. That's it. Just one more component. There's nothing more you need to do. Okay. Then you could construct a quaternion curve, okay? And bear in mind that the length of the quaternion will change, but it will be a four-dimensional vector, okay? And you can construct a quaternion curve, and then you can substitute this back to this equation, okay? Then you will get a rotation. It's always orthogonal, okay? Even if you don't divide by this. If you divide by this, it will be orthonormal, right? All right. So, and here's an example. You have four control points, control quaternions, and they represent four control positions, okay? And then you will get a smooth motion that connect the first one to the last one. If you change this control point slightly, you will move the control position slightly, and the path will also change slightly. It works pretty much the same way as a Bayesian curve. Okay. And you can extend this to B-spline even to two-dimensional motion. Okay. Any questions about this? Now, we also have done work that you can also compute the sweat volume of the tool. It turned out that the Quaternion formulation actually gives you a very efficient algorithm to do that. Rigid body transformations, okay? This stuff is well known, okay? So basically we have a rigid body transformation by rigid meaning before and after the distance between 2 points remain the same, and the angle between two lines remains the same. Okay, basically the body doesn't change shape and form in any way. Okay, this is well known. It maps vectors to vectors and points to points. Preserve the distance, and we make a distinction between vectors and points in kinematics. Okay. The reason being, if you add two vectors, you always get a vector. But if you add two points, do you always get a point? Well, then you will say, okay, what does that mean, right? What's the difference between points and vectors? Okay. One of the key things is point is a physical quantity, right, in space. Vector is a mathematical quantity, right? So if you have two points, you add them, whatever algebra that you want to do. If you change your coordinate frame, the outcome should be the same. Shouldn't be affected by the change of the coordinate frame. Okay. Because of that, there are certain constraints on the coordinates of a point. For vectors, there's no constraint at all, as long as it satisfies the vector algebra rule. That's it, right? Okay, so here is some of the questions that I have talked about. Why do we need to tell the difference between vectors and points, and what the effect that it will have? Okay, so we're gonna. This is one case in point. Points are not necessarily vectors. So we consider we have two points in the plane. One has coordinates 1, 2. The other has coordinates 2, 1. And we can represent these 2 points using vectors. Right? So we get this vector, that vector, we add them. Okay, P plus Q will give you a new point, a new vector, which is 3 and 3. Okay? That's fine. That's what we have learned in vector algebra. Okay? Now let's say we move the coordinate system from here to here, to a new location. Okay? And after we have moved, the 2 points, the 2 points in space in the plane remains the same. Okay? All we have done is we shift the coordinate system forward along the axis. That's all we have done. Because of that, the coordinates that we assign to these 2 points will have to change, right? According to the new location of the coordinate, right? Okay? So 1 is 0, 1, okay? Which is here, 1 is minus 1 and 2. Now, if you add these 2 new vectors, they represent the same point, same 2 points, okay? And then you will get P prime plus Q prime equals a minus 1 and 3, which will give you this vector. We expect these 2 should be the same, right? And for this operation, it's obvious that they are not the same. And then we have a problem, right? Think about you writing a software code to do, when you shift the coordinate frame, you think it's not going to affect, it does, right? Then, we have a problem. So that means, and all we have done is, vector algebra operations, right? So, that's what it is. We cannot change. So the only change we have to, what constraints can we impose on the point coordinates so that when we do a shift, a change of coordinate frame, we add the 2 vector, it will give us the correct answer. Okay? Here is the thought process that we have to go through. Okay, it says only valid operational points are, you can add a vector to a point. Okay, so you have a point and you have a vector. Okay, when you add them, it will be a valid operation. And the other one is that if you have 2 points and you subtract them, it will give you a vector. So these are the 2 rules that we follow. So if you impose this rule, so you can see that if we have a point, okay, and if we add a vector to it, and we represent the vector as the difference between 2 points, and we don't know what point is, this point. We know what a vector is, but we don't know what a point is, okay? But this is logic that we go through. Assuming this is a point, okay, and we represent a vector as a difference of 2 points, we add them up, it doesn't matter how many that you add, you can add as many as you want. So we write them in this form, okay? So we collect the common term. So we have this one, then we have the rest. Now it's obvious that the summation of the coefficients of all these points, they are equal to 1. Right? Because the way we construct it. Okay, so what does that mean? That means to qualify as a point, which is a algebraic structure is a little bit higher than a vector, more restrictive, right? Is that the summation of the coordinates has to be equal to 1, and this is called a barycentric coordinates. So as long as your vector coordinates satisfy this condition, you can add them. They will work just fine. Okay. Such combinations are coordinate independent and geometrically meaningful. If you take two of them, let's say, 2 points, P0, P1, the barycenter coordinates between them is essentially C0 plus C1 equal to 1, which is 1 minus T at T that we have used. Okay? If T is a number between 0 and 1, you will get a point between the two. If T is negative, you will get a point on the left side of the 2 points on the line. If T is greater than 1, it will give you a point that's on the right-hand side of the line segment. Okay. Likewise, if you have 3 points, C0, P0, P1, P2, and the barycenter coordinates will be C0 plus C1 plus C2 equal to 1. And that means 3 points forms a triangle. Okay. If all 3 C's are positive, you will get a point inside of the triangle. Okay. If any one of them is negative, you will get a point that's outside of the triangle. Okay. And you can even determine where outside of the triangle that point is, depending on the size of the C's. Okay. Now here's a question: which of the following are valid combinations? Assuming PQRs are points. This one, of course, it is right. Half plus half equal to 1. That works. And this one also works. 1/2 and 1/4 and 2 equal to 1. And this is not. 1/4 plus 1/4 is not equal to 1. This is 5. 1/3, 1/3, 1/3 is equal to 1. That defines the same inchoid of the triangle. Right? And this one, 1 plus 1 minus 1 is also equal to 1. That works too. And that defines a point that's outside of the triangle, defined by P, Q, and R. Okay. Here's another terminology. The space of points, okay, is called the affine space, as opposed to vector space. It has this additional mathematical constraint. This is essentially, summarizing what we have, talked about. A vector space consists of 2, vectors. If you add 2 of them, they, remain the same. Okay. So if alpha, plus beta equal to 1, that will give you the affine space. More on geometric transformations. We have the most general one is linear transformations, which means the matrix, all the elements are linear. Okay. Then we have rigid body transformations, which is it's a subset of linear transformation that preserve the distance between 2 points. Okay. Then we have affine transformation. It not necessarily preserving the distance between 2 points, just to make sure before and after transformation, you still get the correct point coordinates. Okay, remains to be points. That's what it says. Okay, it can be rotation, translation, which are rigid, can be shear operation. That's not rigid. Okay. So these have applications in computer graphics, positioning, modeling, viewing geometric objects, etc. Here's what mentioned, this is mathematical definition of what a linear operator is. Okay? So I'm not going to go through rotation. Of course, they are linear. In fact, they are rigid. Scaling is also a linear operation. Okay. Caffeine, this is a summary of what we have talked about. It maps vector to vectors and points to points. Okay. Linear operation could map points to vectors that are not necessarily points. Okay. And for what we are dealing with in kinematics, it has the rotation matrix plus a translation. That's the well-known rigid body transformation. This is in homogeneous form. This is the same that we have talked about. Shear can be in affine transformation as well, as long as coordinates remains to be barycentric. Okay, that's the only constraints that we have. Okay. Here's a summary of rigid body transformation, and this is well known. Okay, you have a rotation matrix, and this is the constraint. Okay, R times the transpose, or transpose times R equal to I in identity, and we can define inverse for that as well. Okay. Here we require the determinant to be positive to make sure that it's not a reflection. Okay. Okay, so here are the summary. Linear transformation can have rotation, scaling, and shear. Okay, this is rigid, and these are not. Okay. Affine transformation basically is linear transformation plus translation. Okay, translation is a vector. Okay. Not a point. And then rigid transformation is a special case, as we all know. We mentioned about homogeneous coordinates. Okay, the idea is just you have the Cartesian coordinates and you bring it to higher dimensions. And one of the need for that is because Quaternion has higher one dimension. Higher. So if you want to use Quaternion algebra, it's convenient to use homogeneous coordinates. Okay. This one just to show that how do you convert affine coordinates to homogeneous coordinates by adding a additional dimension. And typically we put one there. Okay, it doesn't have to be one. You could scale it as shown by here. Okay, this is more commonly used. All right. What this one basically say, this set of coordinates and the one that multiplied by constant lambda, they actually represent the same point. Okay. Now, if you're thinking about the three, dimensional space, if you have a vector, represent a point, you multiply by that, constant. Essentially, you form a ray from the origin to that point. What you are saying is that any point on that ray, other than the origin, represent the same point, and that's essentially what homogeneous coordinates is. Okay, it's then tied to projective space. Okay. This is essentially what the explanation is. If you pick the last components to be 1, this is the plane that you have, and you're adding 1, it essentially it becomes a hyperplane. Hyperplane meaning it's a subspace that's one dimension less than the space that it's in, right? So this is a hyperplane that you essentially defines a line going through it. Then any point on this line represents the same point. Okay, and that forms the basis for projective space. Okay, any questions? With homogeneous coordinates, this is a well-known homogeneous transform. If you take any kinematics class, you would have seen this. Okay, dual quaternion. So we talked about quaternion so far. It represents a rotation in 3D space. Okay. Then what about a general displacement that has rotation as well as a translation? So how do we represent that? Okay. One way to do is, of course, a rigid body displacement consists of a rotation and a translation, and rotation is represented by quaternion, and translation represented by a vector. Right? So you have Q and a vector, so you have 7 coordinates. Okay, that works and has a lot of applications too. Okay. Now, there is then the question is, why do we need dual quaternion? Okay, for that, which is more complex. Let me just first tell you what quaternion. It's a pair of quaternions. So we have 2. One is the quaternion for rotation. The other one is defined in this way, okay? Where D is a vector quaternion for translation, okay? And we multiply by the original quaternion, and we take half of that, and that will give you the dual part, okay? All right, it's certainly more work. We can get away with Q and D, right? Why do we want to use Q and Q now? It will give you one additional number and more operation. What do you gain by doing that? Okay. Well, one of the things is, what is D? Well, D is a vector that connects the origin of the fixed coordinate frame to the origin of the moving coordinate frame. Okay, as we all know, if we have a rigid body, the choice of moving coordinate frame is arbitrary, right? If you pick a different, if you translate this away, you will get a different D. Okay, right? And that means whatever you do, the formulation that you have will be dependent on the choice of the origin of the coordinate frame. Okay? In some cases, it may not be a problem. If you know where your coordinate frame want to be, it's not a disadvantage. Let's say if you want to describe the rigid body motion in terms of the center of mass, you pick your coordinate frame to be, moving coordinate frame to be at the center of mass, which is perfectly reasonable thing to do. And then that's fine. Okay? Now, what if you want to do computer graphics animation? You have a set of rigid bodies in space, and you want to have a representation of that such that it wouldn't be depending on the choice of coordinate, moving and fixed coordinate. Okay, so that when you the computer graphics frame, I have this. If I change my viewpoint to recompute the whole thing, I should get the same motion. Not, getting a different motion. In that case, we need to use dual quaternions. By doing this, it actually make it dependent to D. Now you say, well, that's kind of hard to imagine, right? Why this is so? Okay, I'll give you an example. If you consider a line in 3D space, okay, and we all know that you can represent a line by the direction vector and a point on the line. That point can be any point on the line. Direction vector is the same, but the point can be any, right? So, and we have learned a long time ago that's not the best representation for a line. And that's why we have something called the Purwar coordinates. Okay, what does Purwar coordinates do? It's line coordinates that do not depend on the choice of line. It represents the line as a whole, rather than a point in direction. And guess what is the Purwar vector? First one is a unit vector defining the direction of the line. Second one is you pick any point on the line, you cross that unit vector, that will give you the second half of the Purwar vectors. This is a four-dimensional version of a Purwar coordinates, basically. Okay? The reason we have half, this is D times Q, is like C cross U, where you see U is a unit vector, C is a point on the line. But this is in terms of quaternion product. Okay? The reason we have half, because of half angle thing. We talked about rotation, right? If you quaternion angle is theta, the actual movement is actually twice. Same as here. That's why we have to put 1/2 to correct that. So dual quaternion is effectively a Purwar coordinates in 4D space. Okay? All right. Now there's actually deeper geometry underneath it. There are papers describing why this is the case and all that. But this is essentially the case. Any questions about this? Now, this is well known. The question is, how do you convert this to quaternion representation? And the first part, the rotation matrix, is represented by this, which we already know. Here we use cap Q instead of lower Q, okay? But it represents a unit quaternion. If it's not, we need to do inverse here, okay? When we conjugate, we assume it's a unit quaternion. Or we can get it. So here is the D, basically, okay? And we represent D in terms of Qs. Now, what's amazing about this formulation is that if we come back here, when we define Q naught in this way, if you take the dot product between these two, if you treat them as vector components, you take the dot product, it will be equal to 0. Okay, why? Because D is a vector quaternion. Remember there's one slide talk about M? Okay, vector quaternion can be represented by 4x4 Skew symmetric matrix. Okay, so if you dot product these two, it will be equal to 0. It can be shown. Doesn't matter what D and Q's are, they're always equal to 0. Okay? Okay, that so Q dot, that just shows there's a unit quaternion. You also have Q dot Q naught equal to 0. Okay? So this is called the, study condition. It's actually a Plucker condition in 4D space. Okay, Plucker line coordinates has that condition too. It turned out that many people think that that has to be the case, right? Just like Plucker coordinates. Okay, u and u naught, u dot u naught has to be equal to 0. Okay, but if we represent D in this way, Q and Q naught do not, the dot product don't have to be equal to 0. This remains true because you calculate the difference between the two. The non-zero part gets canceled out always. Okay, so what's nice about this is that if we want to do motion interpolation in 3D space with rotation and translation, we can interpolate Q and Q naught separately, and if we substitute them back into here, it always works. We don't have to worry about making sure Q dot Q naught has to be equal to 0. Many people think that has to be true. No, it's not. Okay, that's what magic about this formulation makes motion interpolation very straightforward. Okay. Any questions about this? And the other one is all of them are quadratic. Okay, so if Q is a linear function of time, all the Q's, then this will be a quadratic function, right? The degree is always twice. Okay, and this gives you a very nice formulation for motion interpolation, freeform motion interpolation. And also, if you want to deal with mechanism constraints, the geometric constraint associated with mechanism motion, and these constraints are typically algebraic, right? A point has to stay on a circle. When you move, that's a revolute joint, it's sliding joint. All these constraints are algebraic, and if you substitute them in, you will get an algebraic motion, which means that if you pick any point on the path, that curve will be an algebraic curve. Okay, so we have a nice thing in terms of motion interpolation. If we use Bezier Quaternion curve and all, we will get a rational motion. Rational because we have a division by this common term. Okay, so we'll have a rational motion, which means every point on the rigid body trace out a rational curve. But if we deal with mechanism motion, then it will be an algebraic motion. Okay, so this is really very clean formulation. It ends at 10:30, right? So planar quaternions, okay? Now, we mentioned that in the plane, complex number can handle planar rotation very well. In fact, the best algebra, there's nothing better than that, right? The question is, what about we have a planar display has a rotation and a translation? Complex number, obviously, you can use that too, but it's a combination of complex number and vector algebra, right? So the question is, can you use a version of Quaternion to do that? And the answer is yes. It's a special case of a dual Quaternion. Okay, so this is the algebra. Ij, k's are Quaternion units, and the epsilon is the dual unit. Okay, So they work very well. What's nice about this is that you can formulate everything using dual quaternion. And union quaternion is a special case where the dual part is equal to 0, and planar quaternion is also a special case. Okay. So this is the mapping. We talked about the formulation for defining dual quaternion is D times Q, right? This is the planar version of the same thing, D times Q. Okay. This is a homogeneous form for point coordinate transformation, and this is for line coordinates transformation. You could see that they are almost the same. They are very, very similar. Both are quadratic. Okay, that means you can represent points and line transformation in the same way. Okay, because points and lines are basic geometric elements in the plane. Right, movement of point and movement of line. So this gives us we actually use this representation to represent 4-bar linkages. And here by 4-bar, it's a combination of revolute and sliding joints, not just 4-bar with all 4 joints are revolute joints. The question is, how do you come up with a kinematic formulation that they can be handled in the same way, whether you have a sliding joint or not. But if you use plain quaternion this way, we have different diodes, RR diodes, PR diodes. P represent the translation. RP diodes and PP diodes, they can all be represented in the same way, and that's our goal. All kinematic constraints of diodes can be viewed as line or circle constraints. Okay, either a point stays on the circle, or a line has to be tangent to a circle, etc. Okay, so these are the RR is a state of PR motion for which a point stays on the line, RP motion for which a line passes through a point, and PP, the angle between two lines remains the same. So I just want to, here we try to represent a circle with 3 points. That's well known, of course. And when the 3 points lines up on the line, of course we get a line. But the key thing is that the representation of the circle and line, they are data driven. They are driven by the points that you have. So we want to have a formulation that's data driven, okay? Because we don't know if I give you 5 position, let's say you want to synthesize a 4-bar linkage. Should we use revolute joint or sliding joint? Before we'll say we use revolute joint, we tried. If it works, it worked. If it doesn't work, we try sliding joint. We want to make the choice of revolute or sliding joints to be computed, not choice by the designer. It's defined by the data. If the 5 position orient in certain way, you will need to have a sliding joint instead of revolute joint. It has to be data driven. Okay, so this is the analogy that we have. Okay, we want to have a formulation of a circle that can be a line, but is determined by the data. Okay, and we just want to extend this to 4 position or 5 position synthesis. Okay. So here we basically use a homogeneous representation of a line, and which when one of the coefficients is equal to 0, this reduced to a line. This homogeneous representation of a circle. Okay. All right. So here's the key. Whether 3 points determining a circle or a line is determined by computation, not by selection. Okay. So we basically extend this to diodes. Okay. This the constraints can be a circle or a line. Okay. Then we substitute this Quaternion representation there, and we get this quadratic form. And I'm going to run through this. Okay. So in the end, it's basically we have a quadratic form which is fairly general. Okay. And then with two additional constraints. Okay, Q's are the unknown parameters. Define this quadratic surface. It's a special quadratic surface that meets these constraints. As long as this is the case, it can be a R diode, RP diode, PR diode, PP. They're all the same thing. And this is going through. Okay. Then what's nice about this is we can develop algorithms that can do type and dimensional synthesis simultaneously. Okay, so that's one of the advantages. So I'm running out of time. This is we can compute that volume. I don't have time to go through this. Let me just talk about the Clifford Algebra, since I'm running out of time. Now, Clifford Algebra is basically based on vectors. I mean, Gala is called a zero vectors, and it has one component. Okay, then you have one vectors. This is the typical vector that represent points. Then we have bivector. So what is a bivector? Because if you look at space, you have points, you have lines, you have planes, right? So, bivectors are representing lines, and then we have trivector represent the planes, etc. etc. So we have an algebra of geometric entities, right? We have points, lines, and planes, and hyperplanes, and all this stuff. Then we have a unity, which is one. So how do we define a algebra that can handle all these quantities? Okay, that's essentially what Clifford algebra is. Rotation, translation, dot product, cross product. Okay. Now, a well-known result of the Clifford algebra is the vector wedge product that it's used in multilinear algebra. That's sort of a well-known. But in terms of Clifford algebra, most of the basis vector constraints are the same. If you j times I equal to I and j by negative sign, same as Quaternion units, okay? And square of each one can be either positive or negative. If it's negative, you will get a Quaternion algebra. If it's positive, you get something called a double algebra. So there's another thing that actually works. Okay. If it's equal to 0, it actually also works. That will give you another algebra. There's interpretations of all this stuff. Okay. So what I want to say is that Quaternion algebra is a special case of Clifford algebra. Okay. And the multilinear algebra, the wedge product, is also a special case of this. And so if you use Clifford algebra, that you can handle pretty much everything you want to handle in kinematics. Okay, so with that, I end my talk.
Thank you.
I will make my slides available. I'm sorry I didn't have time to run through the rest of it.
All right. Any questions for Professor Deb? You guys just want to get your coffee. Okay. All right. Thank you. So a couple of housekeeping items. If you did not register for the summer school on the website, so you don't have your name in that case, we have certificates to give in the evening. If you are participating and you did not register, please let me know, okay, so that we can prepare a certificate for you.
Right, this is getting very cold.